Okay guys, welcome back. Last lecture we start looking at or learning how to build the software that manages a database, alright? So we mentioned that one important thing is the ability of the database management system in order to handle or deal with the very large amount of data. Alright? So we start last lecture, we take a look the way how the database management system or computer system can store and manage very large amount of volume of data. Okay, so this is the first major problem. Then after that, we said we are going to look at the what representation and the data structure best support efficient manipulation of this data. So we're still in the first one. How does the computer system store and manage very large amount of volume of data? We didn't cover this one more details, but to start looking at this issue of this problem. How the database management is going to do that. Okay, so we began with the technology used for the physical storing massive amount of data. We looked at the disk, okay, with the secondary storage as a disk. We look at the way how the disk can be accessed, how it can be performed, or compute the access time. This is the most important thing that we look at last time. We went over, the components of the disk. We look how it looks like on the side, how this data can be stored where, how can you identify as a blocks, in other words, in sectors. Then after that, how can you identify which block, which data can be accessed in order to retrieve the data that I'm looking for. Okay, so we'll just remind you, for example, if you have a 120 block and the block does not exist in the main memory, we need to compute the access time. That's what we did the last time, right? And the reason behind that, remember, the main focus in this class to do what? Disk-oriented database management system. The assumption that we have, the entire data must be stored in the disk, right? It must be residing in the disk. Every time we need the data to be operate on specific block, we need to fetch this data from the disk to the main memory in order to operate on this data. Okay, fetching the data from the main memory is expensive operation. So we need to figure out a way or some techniques will help us in order to mitigate this effect, fetching the data from the disk. In other words, looks like if we manage to give illusion to the user or the application that whatever you're looking for is going to be available in the main memory. Okay, of course we have some techniques, data structure, mechanism allow us in order to figure out to have the best way in order to achieve this goal. Okay, so again, we talk about the accessing the disk. In order to access the disk, that means we need to perform the following. First, we need to read the block from the disk. Okay, in order to do that, you have to make sure the disk can be start spinning. That's what is called. We talk about this one here, the seek time. Okay, the seek time is measures. Let me go to the next slide here. We have, let's say, yeah, this one here. In order to compute the access time, when you're looking for the block is not available in the memory and the block is going to be available in the main memory, we have to perform the following, time, our operation. First, seek time. In other words, you need to find a way or make sure that this starts spinning and the arm has to be moved to the correct track, to the disk. So you find the exact cylinder of the track. Or in other words, the seek time is going to measure the delay for the disk head to reach the right track. How can you tell the right track? Because the system knows the block that you're looking for in the track 5, 6, 7, or whatever. So you have to move the head there. That's the seek time. Then after that, we talk about the rotational delay. So what does it mean, the rotational delay? The disk head must be wait until the right location on the track is found. In other words, it's going to be what? Computes the time to get the right sector or the beginning of the block in order to start reading. Yeah. Then after that, the last time is transfer time. With the time, is going to do what? The time that is going to be computed, that the disk block can start reading from the disk and copy to the memory. In other words, the transfer time is computed as what? Is try to compute how long the actual data read or write takes. Yeah. How many times that you're going to perform here. We went over this one. We said last time we have many ways in order to how to compute the seek time, rotational delay, and the transfer time. Most of the time, the seek time is going to be given to you, or maybe give you an equation to how to solve this one. Rotational delay, you need to compute how. You need to know how to compute this one using the speed or the rotation per minute unit. The value that you're going to give in the question. Transfer time, you need to compute the transfer time based on what? The transfer rate and the block size that you need to retrieve. or we can use the rotational delay in order to compute the transfer time. We're going to give you an example. The most important thing I want from you here, this is the most, the slides that you need to make sure that I'm not going to say memorize, but you understand. I'm not going to ask you any question related to something bad, whatever we covered before. The most important thing I'm looking for, this formula, because how can you compute, the access time? I will give you an example here, okay? We went over this one, we give you examples here. One thing before the example here, we looked at the way how can we try to enhance the seek time? How can you make it speed up the access to the data? Because every time, if I'm trying to access the data, I need to compute, the access time, that's going to be expensive operation, right? Because the access time requires you have to compute the seek time, rotational delay, and also the, the transfer time, right? So it depends on your location. How can you organize the data in order to enhance this operation, in order to make this one fast operation, okay? Or in other words, we try to lower the disk input output operation in order to perform, in order to access the data or fetch the block from the disk, okay? How can you do that? Take a look at how to reduce the seek time and how to make sure reduce, the rotational delay. This is the most important thing. Why? Because based on the, the graphs, the diagram or image that we have here, we saw that the seek time is almost between 0 to 10 milliseconds, and the rotational delay at the same time, and the transfer time is going to be less than 1 millisecond. So it looks like we need to find a way in order to enhance the read-write or lower the disk input output operation cost. We need to come up with a way in order to reduce the seek time and the rotational delay. So right now we said, we're looking for one block, right? At random. A block is going to be a specific location. How to fetch? You have to compute this one. How about if you said the next block? For example, the system said I need to block 1 and block 5, or block 1 and block 2. I need to access them. I need to fetch them to the memory, the main memory. So if block 1, it looks like you're going to perform a random access and to read the block 1, access time, seek time, rotational delay, transfer time. Then now, after you transfer the first block, you need to find a way, how can we access the next block? All right? The best way in order to do that, we are going to try to arrange the data sequentially on the disk. So what does that mean in this case? So it looks like, assume the disk, I will assume this is the track. Of course, the track is a circuit, but I'm going to do it as a line to simplify the process. So here we have one block, let's say block 1. Then once I've done a block 1, I will store block 2 next to the block 1. Then after that, I put block 3, and etc. So what's the plan here? When someone try to access, for example, block 1, block 2, block 3. So what I need to do first, I need to access, perform seek the access time in order to reach block 1, right? Seek time, rotational delay. Then after that, it will transfer it. Once I done transfer the block 1, this is, the benefit if you store your data sequential next to each other. Once you read the first one, you see, do you need to have a seek time and rotational delay? No, there is no need. Why? Because at the time, once I've done reading the first block, I found myself at the beginning of the next block. So the only thing I need to do, what? Transfer. Yeah? Once you finish transferring, reading the entire block 2, I found myself at the beginning of the next block. So that's the way. If you store the data sequentially, it's going to help you in order to reduce, or minimize the cost of input-output operation. Make sense to us, guys? Okay. So the next block concept, yes, that's what you do. One way in order to put the stuff. But remember that the fragment is a different story. Here, the database management system, the one is going to take care of this operation. Okay? Here, because who's going to generate a similar operation, but not the exact one. Because the operating system and not this fragment is doing what? Try to put the data that belongs to the file in one place. But here for the database management system knows exactly which the next block. For example, what if I want to sort the data based on the tuples and store this one in sequential in sorted order? So using the database management system, the one is going to take care of this operation. Because now the database management system, we're going to explain this one later in the next part of today's lecture, where you say why we cannot rely on the operating system and rely on the database management system, because the database management system knows exactly what's going on, what is the content of these data. Okay? So kind of you can say similar, but not the exact operation. So when you talk about the next block concept, the best way to store the data sequentially, you're gonna use what? Use the same track first. Okay, you're still in cylinder, the same cylinder. Put the data in the same track next to each other. Once you're done, go with the next surface, all right? We have to, in the platter, we have two surfaces, the top surface and the bottom surface. Yeah, so we're gonna store what? The same track in the top, next surface. Then after that, jump to the next platter. So we stay in the same cylinder, the same track, the same cylinder. Then once I store this data in the same cylinder, what I need to do is I need to jump to the next cylinder and do the same operation. This is the best way. Why? When you access, especially when you perform sequential access to the data, sometimes it requires from you to read the entire tube or blocks that belongs to this file or this relation. So if you put this one in the same cylinder, using the next block concept, you're gonna access the first, perform only one seek time. Seek time. Then after that, rotation delay. Then we reach to the beginning of the first block. You're gonna read to the right cylinder. Once you read the first block, you find yourself in the next beginning of the next block. Continue. Read the next. Read the next. Once you're done here, you reach to the beginning of the first block that you read. Then here you didn't need to move anything. Now the header is going to start reading from the next surface. Once you're done, jump reading the next platter, the surface from the next platter. Once you're done from this one cylinder, the only thing you need, maybe you need to require for you to move to change to another cylinder with another time that you're going to perform here. So for the sequential scan, since the system knows exactly the data going to be stored next to each other, prefetching is going to help us in this case. We're going to see later how modern database management system achieve this goal in order to make sure that reduce the storm when there's someone on the query engine looking for the block, and the block is not available in memory. You need to figure out a way. Since I know this query is going to perform like sequential scan, so I know in advance that, oh, looks like I'm going to read the entire blocks that belong to this file. So I'm going to, while I fetch block 1 or block 2, I'm going to maybe, since you have a space, I'm going to fetch block 3 and 4 in advance before the query engine asks for them. Okay? Good. So if we do things right, for example, we have a double buffering. If we have a double buffer, we're going to talk about this one later. We have two buffers in this case, two locations in the memory in order to just fetch the blocks, staggering blocks put next to each other. Okay, so the time in order to get the block should be proportional to the size of the block. That's what we did here. I'm talking about the next block. When you read the first one, you read the first one, you're going to do the access time. Once you're done reading the first block, you find yourself what? In the beginning of the next block. So the only thing you need to do what? Just you need to transfer. All right? Transfer time. You have the block size here divided by the transfer rate. And continue doing this one. We do have some extra time negligible based on the transfer rate. Why? Because sometimes you need to move, for example, from, let's say, you're going to skip the gaps. Maybe you need to change from, let's say, once a while, change from, for example, to the next cylinder, either this cylinder or this cylinder, and etc. Okay? You need to switch tracks, for example, from the top of the first platter, the first surface to the next surface. That's another thing. So the time compared to the seek time and the rotational delay is going to be negligible. So the way that organize the data is very important. It's not random. So we talk about this one, I think, in the beginning of the last lecture when you said that. Let me go back, I think, to the slide, if I remember. Let me go back to which slide you said that. Let me go here. Just to remind you with the question, you said we're going to get back to the slide. I didn't recall the slide now. Number say. I didn't find it, definitely somewhere. Anyway, we talk about the way that organize the data on the desk is going to affect the overall performance. So in other words, you see, if you just scatter your data everywhere randomly, block 1 is going to be, for example, cylinder 1, block 2 is going to be cylinder 15, block 3 is going to be cylinder 5. So when you read the entire data, now we have a problem because you have like what, most of the time can be wasted just to find out which is the beginning of the block that you need to fetch next. But if you put the data next to each other, the way that organize the data is going to affect the overall performance. And that I show you the example here. You see that? If you put this one data sequential next to each other, so it's going to be minimize the number of disk input out operation. I mean the time spent in order to fetch the next blocks. Okay? Of course, there is a cost because you need to make sure that every time when you store your data, you need to make sure the data is going to be stored as the next, blocks next to each other. So there's a time. It looks like if you try to keep your data sorted, there is a penalty because you're going to spend some time processing the data to make sure the data will be sorted. But at the end, when you read the data later, yeah, it's going to be so fast. Right? Okay. So as a rule of thumb here, sequential access pattern, sequential access or input output is going to be much faster the random input output. So what do you mean the sequential access pattern in this case? Is defined as successive, requests for successive block, disk block. So in this case, I need to have, for example, block 1. It doesn't matter block 1, 2, it must be the same order, but I'll give you an example, 1, 2, 3, it's going to be easy just as an example. Block 1, block 2, block 3, and etc. I need to access this block. Okay, so in this case, once we access a block, I'm going to find myself in the next beginning of the next block. So it's easy for me to read the next block and etc. Okay. In other words, in the sequential access, generally speaking, we are going to what? Access the entire relation most of the time to perform this, when you say select a star from the relation R. Yeah, if the data is stored next to each other, the sequential access is going to be much faster than index access, even using the index. We're going to see this one later, how it works and why this is the case. And the simple thing you can imagine, because right now, the only thing you need to perform only one seek time, access time, then after that, the rest is going to be just transfer, right? And you have some, negligible time that maybe sometimes from time to time need to jump or change the track and jump to the next cylinder, okay? That's why I said the task or seek time is going to be only for the first block. The second one, the random access. So the random access, assume that you have access block 1 and the block 5, then a block 2, then a block 7, for example. And assume when you use block 1, 5, 2, 7, means that this block is going to be in the first cylinder, and this is going to be the 5th cylinder, and this is the 2nd cylinder, and the 7th cylinder. If you just as an example to simplify the process. So you see that right now I need to jump to the block 1, the cylinder 1. Then after that I need to jump, for example, to what? For example, to the cylinder 5, to read the block 5. Then after that I need to back, you see, to 1. You see, back and forth. You have to perform access time. This is expensive operation. Then after that you need to jump to what? To the 7. You see that? So it looks like I have a zigzag, back up and down, up and down. This is a bad idea. This is going to be cost, right? Because the transfer rate is going to be too low, since most of the time you're going to spend in order to what? In order to just to find out the beginning of the block, that next block that I need to fetch. So this one is going to be bad idea, and the performance is going to be much less, expensive. And this one, this one bad idea, and this one is going to be much better. Okay, because the time is going to be much less. So we prefer to have a sequential access. In other words, we try to find whatever we can do or come up with whatever data structure, organization, techniques that allow us in order to reduce or minimize the cost of disk input output operation or access the data from the disk. Sequential, that's a great idea. So if we do the data sequential, when you access the sequential, you see that compared to the random. Yeah. So the way that they lay out the data of the disk is going to affect the overall performance. And our goal, starting with the first day until the last day of this class, we try to minimize the number of the disk input output operation number and cost. Okay. So what are the costs if you try to write from the remember the reading, that means the operation take from the disk to the main memory. To the main memory or to the buffer pool, right? There's, read input out operation, or the I was just before just to say IO. Okay, writing, this means you have a block in the main memory, you perform some modification, then now we need to reflect the change to the disk. So this is the writing here. The cost of the reading is similar to the writing. What you need to do here, we have a block in the main memory, and you need to identify where the block can be stored in the disk. So you have to specify the beginning where it's going to be there. Yeah. Then after that, you have to perform set reading, transfer the data from the disk to the main memory. You're going to transfer the data from the main memory to the disk. The cost is going to be the same, unless you wanted to verify. You need to make sure that double check the data has been reflected to the disk. So in this case, you need to perform one add rotation, full rotation, then you need to read the data again. Why? You see that, for example, this is the track here. This is my header here. I just here specify the beginning. Then now I do what? I just install or say write specific block. When I write specific block, the read write header is gonna be here, right? Because this one is gonna be moved. Now, in order to read this one to verify, I need to perform the one full iteration. And to the beginning of the block I just write, it's gonna be under the head. Then after that, I'm gonna read it, then double check in the main memory to see whether the count is okay or not. That's why I said this is, the cost for the writing, if you want to verify. In order to modify a block, the same thing here. It looks like reading and write. In order to modify operate on the block, we cannot operate directly in the disk, right? Although there's some technique try to do some kind of operation in the cache and etc. But different story here. Just let's go with this case, worst case scenario. Generally speaking, we cannot operate directly on the data on the disk. So I have to fetch this one reading to the main memory. That's what you're gonna be. So you have to read this one to the disk or read to the buffer. Then after that, modifying them in memory of the buffer, whatever operation you're gonna perform here. Then after that, you need to write it. There's the cost. Then after that, if you want to verify, there's another cost gonna be involved in this operation. Good. Let's take a look at one example with the one that expects similar to one that you expect in the exam. So this is, I show you two slides, very important that you need to focus in this chapter. I will try to give you but this symbol in order to make sure that, because the content of this class is too much to cover. So mainly I'm gonna say you need to understand everything, but you need to focus on these slides in the exam to make your life easier, okay? So here, expect that you give you some description. I expect for you to compute the access time. Okay? So in this case, let's take a look here. What do you have here? And you do have the time that we have. Let's take a look here. We do have that, let's give an example, the rotation per minute, how the speed, velocity of the platter or the disk can be spun. Okay. And you know how to compute the rotational delay from this one, all right? This is an example. Assume that we have one surface. So that means we have one platter, one surface. I know it's a weird example. Yeah. Generally speaking, disk has up to 3 to 5 platters, and they have two surfaces. Yeah, each of them. But here, just to simplify, come up with a weird example. We have one platter, and we have only one surface. So there is no two surfaces. Good. And we said here the size of usable capacity is 16 megabytes. Okay, give you the usable capacity in the system that we have here. Okay, so and also we said what here? Give you we mentioned that we have the number of cylinders given, 128, and we have the seek times given, and sometimes give you maybe extra information. Maybe you don't need them. Okay, so in this case, I don't need to jump to the next cylinder here. Yeah, but if the required from you, the question said, we're in one cylinder, now you need to jump to the next cylinder. You need to compute the time or delay. So you can add the number 5 in this case. So anyway, so you have the seek time is what? It's 25 milliseconds. The number of cylinder, 128. And here we have the usable capacity. And here we said one block can be one sector. So that means just a symbol, just an example. Assume this we have one sector. This is the gap. This is the second sector, this is the gap, and etc. And we assume that one sector is going to be one block, okay? And the size here is going to be 1 kilobyte. So the size of each sector is going to be 1 kilobyte, right? Based on the data here. We give you an extra piece of information. We said 10% overhead between blocks. What does that mean here? That means we said the gaps represent 10% of the entire circle, okay? So the sector is going to represent the rest of 90%. Okay, so when you perform one rotation over let's say one complete rotation, 10% is going to be over unusable data. Okay, we'll see how can you use this one later. So this is the numbers, and the nice thing or easy thing to work with using the binaries. Okay, 2 to the power 20. If you have, for example, 1 megabytes, kilobyte, I mean 2 to the power 10 multiplied to the power 10 here. Okay, and here we have 16. You can convert this one to the power 24. The cylinder is going to be 2 to the power 7. It's easy to compute the numbers. By the way, in the exams, I don't care about the final answer. I do care, especially in this one. I care only about the right formula, and you plug the numbers, then done. I'm not gonna judge you, penalize you whether you are, let's say, human calculator or not. Okay. So even if you didn't convert this one, the most important thing for me here up to here. For example, if you ask you to compute, I mean, the capacity of the cylinder, then if you write this formula, then after that to plug the numbers, I didn't care about the rest. Okay, it's not important, I mean. If you made a mistake here, that's fine. That's what I grade here. Anyway, so now I need to remove this one because I need it. I need to write something. So anyway, so here we have the number of cylinder 128.7. Okay, the capacity of the cylinder can be computed as following, right? Okay, the capacity can be what? The total capacity that we have in this case 2 to the power 24 with the size given in the example, divided how many cylinders do you have? In order to, since we have 128 cylinders, I know the total capacity of the disk, divided the number of cylinders is going to give me, for example, the capacity of each cylinder. I know this weird number. I think I need to change this one and have a different numbers because now 128 is going to be confuse us. We know 128 as the number of cylinders. Now we have the capacity of each cylinder is going to be 128 kilobytes. And later we're going to see the number of sectors, blocks within the cylinder. In this case, is going to be 128. Hopefully it's not going to confuse you, these numbers. Anyway, I compute the capacity here. For example, if I ask you to compute how many blocks do you have per cylinder, we know in each cylinder what? It's going to have what? It's going to be, remember, in cylinder here we have only one platen, one cells. So it looks like I need to compute how many sectors per track, in the track, right? We do have a sectors here because we said one sector is equal one block that's given here. And they give you the size of the sector, 1 kilobyte, right? So you take the capacity of each cylinder, which is 128 kilobytes, divide by the size of the block, or the size of the cylinder, because in the first scenario, we assume that one sector equal one block, right? Then after that, you compute this number, divide this number, and end up we have 128 blocks. Okay, so far so good. Good. So now I need to compute the access time in general. But before I compute the access time, I just to perform some computation, yeah, just in order to make sure that we are on the same page. Just try to simulate, for example, what if I ask you, for example, the time over useful data? What if I ask you about the time transfer, the time for one block with gaps, without gaps, etc. That's kind of a questions, okay? So I need to make sure that you're prepared with any kind of question you can answer this. They are easy. The only thing you need to find out what the actual right formula that you need to use. Okay? So the first thing we need to look at here, how can you compute what is called, the rotational delay. We talk about this one, the rotational delay, right? We said the rotational delay or latency is going to be half of the time it takes of this to make a complete rotation or revolution, right? If the disk spin, for example, 3600 rotation per minute, we need to convert this one into the second. Then after that, you need to compute this one in order convert this one into to be milliseconds in order to have all the units going to be in the millisecond. I give you the simple formula last time, and here just you need to do the following here. So you take what here? You take, for example, here 1000 with millisecond, okay? Multiply by 60 seconds, or let's say go with the easy one. Took 60 divided by, let's say, 3600 here, yeah. Then after that, I need this convert this one to the second, and here multiply by 1000 in order to convert this one to the millisecond. Okay, so we end up we have here almost 16.66. This is the time, or let's say one revolution or one rotation, right? Remember, rotational delay latency. I didn't compute this one. Rotation. The rotational latency can be take this number and divide it by 2. Okay. So again, take the disk span value, take 1 over this value, yeah, in order to make which is going to show you the time to make one revolution. Then after that, you convert this one into seconds, and after that to to millisecond in order to have the same formula. The only thing you can see, use this formula. The only difference you change with this one or substitute this one with the value that's given here. Good. So let's take a look at the time used over the useful data. So here we have one track. They have one sector, and this is the gap. One sector, one gap. Yeah, and etc. Of course, the track will have something like this, but this you have to do this one in linear or one line. It's gonna be easy to understand. The one block is gonna equal one sector. Good. The time over useful data. What does that mean in this case? The time that's gonna be the head that's gonna be passed over the useful data. So this one can be performed one rotation, yeah? And I know one rotation that's 16.66. 90% of the time that's from the 16.66, it's gonna go over useful data because it gives you this one hint in the the example, 10% over, let's say, unusable data. Okay? So in this case, you take this number, multiply by 90%, it gives you 14.99 milliseconds. The time gonna be spent to go over all useful data, over the sectors. Okay, the time over the gaps. That means you take the same number here, and 10% is gonna go over what? Unusable data. Okay, which in this case is gonna be gaps, can be computed at this. Good. Now I need to compute the time to transfer one block. In order to transfer one block, let's do different color here. In order to transfer one block, what you need to do is going to be random, right? In order to transfer one block, do you need to have a gap here? No, it looks like you need to compute the time to transfer, let's say, a sector. Because one sector in our example, in this scenario, equal one block. So you need to time just go over here, this area, all right? So in this case, you can take what? Useful data, 14.99, okay? Divided by how many blocks do you have here? So the 14.99 divided by the number of blocks that we have, which is going to be the time that we spend in order to transfer one block. I don't have the data rate or transfer rate. If I had a transfer rate, I can use the size of block divided by the transfer rate. Or we can use, remember, we talk about the transfer rate, we define this one as what? Sorry, transfer time. Is the time it takes the sectors of the block and any gaps between them to rotate past the head. So that's why I use, the time based on what? I don't need to include this, let's say gap here, because one block is going to be one sector, I need only useful data. Or someone is going to say, okay, I can use 16.66 divided by 128, and this one I need to use 90%, because 90% is going to be useful data, and 10% is going to be unuseful data. It's going to give me the same number. Clear, guys? Okay, I would be happy now since you applied. Thank you. So the second one, if we try to compute the time the transfer time of one block plus gap. So in this case, you need to what? I need to block plus gap. So in this case, I'm going to use what? 16.66 divided by the number of blocks that we have in order to give me this time. Okay, those are things. Maybe in the exam, I'm not going to give you like, let's say, 10% useful data and unuseful data. Make it easier for you. But you need to find out the way how to compute the time based on different scenarios. We have one block equal one sector. I need only to fetch or transfer one block. Do you need to include the gap here? No, because it's gonna be random. The only time I need to compute this block here. I don't care about this gap because it's not gonna be part of the transfer. Or if the block is gonna be composed of more than one block sector. So in this case, this is a different story. It's gonna be show you in the next slide. In a few minutes actually. Okay, so let's take a look here. I need to commute the access time. So we have to take the seek time, rotational delay, plus the transfer time for one block. In order one block, this access time to one block, okay? So the seek time is given, 25, and the rotational delay is gonna take, take the half the time that computes in order to compute or complete one rotation. We did this one 16.66 divided by 2. Then we have what? The time that we need to spend in order to what? In order to fetch, or in order to, let's say, give me a second here. In order to what? In order to transfer one block without gap, because the block here equal 1 second. Okay? Add these numbers, keep this one 33.45 milliseconds. Okay? And the question here, why we need to use, the time it takes to transfer one block plus gap here. Why we didn't use this one? Because we said 1 sector is equal 1 block. And this is a random block. So the only time I need to do here, I need just to fetch one block, sector. I don't need to consider the gaps here. That's why I use the time without gaps. Okay? Let's change this one, the scenario that we have. Assume that one block is equal 4 sectors. Oh, the story is changed now. So this is just an example here. So assume that we have here this one sector, yeah, and this is the gap, the second sector, the gap, the third sector, the gap, and this is the fourth sector, yeah. So this is one block. In order to fetch this one, in order to compute the access time here, the access time to access the block here. So you need to find, and the head is gonna be must be in the beginning of the first sector, right? What we're gonna do here? You're gonna use the sector plus gap, then sector plus gap, because the time is gonna be computed. Someone gonna say, can I exclude the time that when the head is gonna be passed through at the top of the gaps? No, in this case, because it's gonna be time is gonna spend in order to what? In order to fetch the entire block, and the block composed of the 4 sectors. So the count, I'm going to count the time that's gonna be let's say the head is gonna be passed over the gaps between these sectors. So here we have one sector gap, sector plus second gap, sector plus the third gap, and here I need what? Only sector without gap, because up to here this is done. This is the entire block is over, and that's the time that I need to do. Need to count. Do you need to include the time here for the gap? No, because not gap. After that, there's no data. I need to read them. Done. So in order this one, so it looks like you need to what? You need to take the time, read 1 sector plus gap, yeah, or 1 block plus gap. So I need to compute this one 1, 2, 3 times. That's why I said 3 multiply the time that we have. If you take a look here, we see that 1 block plus gap, or 1 sector plus gap, gonna be computed by 60.66 divided by 128. Right? This is gonna be 3 times. In order to compute this one, 1 with gap, second with gap, third with gap. Then plus, I need only to have time without gap, or transfer time for 1 block or 1 sector at the time when you have 1 block equal 1 sector. It's gonna be here what? 14.99, hopefully the same number, divided by 128, which is gonna be multiply 1. That's why I said this one plus 1, it's plus 3. This is the time here, 33.83. You see that here, if we compare this number with this one when the block equal 1 sector, you see that we spent we spent here 33.45 milliseconds in order to reach 1 block or 1 sector, right? Here, when you increase the size of the block, we end up, we have what in this case? We have almost the same time, yeah. Yeah, actually, the exact time which allows me to read the block that composed or contains of 4 sectors. The size, that's why when you say that 1 sector, we're not going to use the sector as a unit in order to achieve the data. That's why we're going to use the block, and the blocks, generally speaking, are going to be composed of more than sectors, or 2, 3, 4, 5, 6 sectors, in order to what? When you're using the data as a block, it's going to save us a lot of time. Okay? You need just to think about what's the time that you need to compute the time to read the full track. Okay? It's easy. If you understand this one, you can come up with a way how can you compute the the time to read the full track. Make sense, guys? Clear? Good. Thank you. Yeah, 25. Take a look at it's given here. I said here's going. You see that? We said the seek time, the average 25 milliseconds. Okay. So you need to focus on the formula, and also you need to focus. This is an example. It's gonna help you if the star is still there. That's what I need from you to focus in this chapter, in the exam. Okay, good. So what else now? Let's take a look. See how can we perform, consider some techniques in order to reducing the time it takes to read or write data from the disk. One technique we can go over this one here is like you need to do some optimizations, okay? And one optimization or set of optimization you can do the following. You can use a disk scheduling algorithm, okay? For example, elevator algorithm. I'll just give you an idea what's going on in this one. Then after that, maybe go with the large buffer in order to allow you to fetch more data. For example, my buffer allow me to only fetch, for example, 10 blocks. If you have a larger buffer, which allow me to fetch or store, let's say, 100 buffer or block, that's great, yeah? Of course, that's gonna cost you because you need to reserve memory space in order to hold the data here. Be fetching. With one interesting thing, the most modern database management system, once you're gonna see later, gonna be smart enough in order to identify what kind of query that you need to perform or can be executed. And based on the query, you're going to say, oh, it looks like there's a query fetching or reading the entire data perform sequential scan. So in this case, if we have, while the user or the query processing some data, I'm going to do what? I'm going to fetch the rest of the blocks or more blocks in advance. So when the user or the query engine starting or looking for that page, so new blocks, the system is going to say, here you go, it's available in the main memory. You see that speed up the process. You can use disk array or maybe use on-disk cache. This is another techniques. Of course, the main thing is not our concern here. I'm just the most important thing you need to focus on the prefetching here. Okay? So let's take a look at the disk scheduling here more. So the disk schedule in this case, we need to have like for each disk as you study in the operating system. For each disk, it has a disk schedule in order to take care of the request, okay? From the high level, some query will say programs to say, I need this block, I need this data, I need this data. This disk schedule is going to have like service policy. In this case, in which order the disk controller is going to process these requests, okay? We have a simple techniques. The simple one, or the two techniques we need to cover. One of them is the naive solution. The first come, first serve. So in this case, we end up, for example, assume that in the high level, we said, okay, I need a block 1, I need a block 5, I need block 7, I need block 2, and etc. So the system, we're going to say, assume just to simplify the process. A block 1 means, the first cylinder, 5 the fifth cylinder, 7 the first cylinder, etc. So you start from 1, take the block 1, then after that, jump to the 5, then after that, jump to the 7, then after that, maybe back to the 2. Yeah, you see that? It looks like you're doing zigzag in order to execute the query. This is a bad idea. It's fair, first come, first serve, but it's going to be cost us time. We need to have a smart techniques, better way. It looks like that's what is called the elevator here. You know the elevator, when you try to take an elevator in any building? Yeah, of course, don't trust the elevator. Don't take the elevator because most of the time the elevator is going to be defective. Okay, so it's a good idea to use the stairs. Anyway, in this case here, the elevator has nice techniques. While I'm still in this floor, I'm looking to say, is anyone wants to take the elevator? Is anyone I need to serve? In other words, if you compare this one analogy, the desk, as long as I'm in the specific cylinder, the disk or the schedule or the disk is going to take a look at this, or this controller is going to say, okay, do you have any request I need to serve while do you need any data from the serve, let's say cylinder 1? If you want, I need to execute them right now. Then after that, you jump to the next. It looks like go up and down. It sweep, through the same thing, the elevator goes from the first floor to the last floor, up and down, right? While the elevator at a specific floor, you try to look around for any serves, right? Anyone wants to get into the elevator, okay? So that's another technique, much easier. It's going to be efficient but unfair, especially if you have someone it's gonna hit the elevator like B, and what they're doing here, for every single floor, just ask for press the button in order to call the elevator. In order to make the people struggle, it takes long time in order to just reach the let's say the desirable level. Yeah, I used to do that when I was a kid. Okay, clear, guys? I'm glad next week is gonna be in person. Yeah, so we can see each other. So that means enjoy your time. This is the last time you're gonna watch Netflix while I'm teaching this class. Okay, the prefetching. That's a prefetching. That's as you mentioned, the database management system gonna have technique, a way, smart enough in order to tell. Oh, it looks like you're gonna be. I expect that you're gonna the next block that you are going to ask, for example, block 5, block 6. It's fetch you in advance. Okay, this is gonna speed up. The data. Speed up the access data up to n factor, where the n is gonna be the number of blocks that be requested by the processor in general here. Let's see an example here. Assume that you have a file, and the file has many blocks, P1 and P2, and so on, or A, B, C, D. Then you need to do what? The program that we have access this file block by block. Take the first block, reading, and the process. The second block, the third block, and etc. in sequence. Good. So this is the single buffer we thought. This is the naive solution. Okay. That means in this case, it's not. The perfect solution. Just to give you an idea. This the simple way how to implement this one. I have only single buffer. So that means in this case, read the data, the first block, from the disk to the main memory. Process this one. Once you're done, now you need to read using the replacement policy. That means in this case, read the next block. Fetch to the main memory, process the next block, and continue doing this one until you finish. You see the first one, process the data, then fetch the second block to the buffer, and process the data. Remember, assume that we have only one single buffer to simplify the process. So here we have P1, fetch, process, then after that done, B2, fetch, process, and etc. Okay, so let's have some notation in order to see the cost of this one. Assume that P represent the time to process a block, and R is going to be the time to read one block. Okay, and we assume that we have n blocks, so from P1 up to Pn. Good. The time in order to read one block request, in this case the first one, it's going to be R. Right? You have to spend minute or second, whatever, to fetch the block from the disk to the main memory. Good. Then for the first block, then after that you have to process this block. This is the first block. For the second block, you're going to perform the same operation, R and B. So it looks like we need to repeat this operation n time. And this is the time it's going to cost us in order to read and process the entire file using one buffer. How about if you have a double buffer? So the double buffer is an interesting idea here. So in this case, assume that we have two buffers here. They say 1, 2 in the memory, okay? So the data, first you're going to read one block. I know we said B1, B2, B3, B4, or we can say A, B, C. Let's say B1, we have the same example to be in the same size. The same size. B1, B2, and etc. First, you fetch the first block B1 here. While you're processing B1 here, the system knows, oh, I have another buffer. How about fetch the next block here? Simultaneously. Once the engine, or the query engine, or the process, whatever the application program, finish processing the first block here. What it's gonna do here now? Starting processing the next the block that in the second buffer, right? While I'm done from the first block here, while I'm processing the second block, I'm fetching the third block here. You see that? So it looks again when the buffer is full, program process the data. And at the same time, the more data can be read into what? In another buffer or other buffer. And you need to perform rotate buffers when done processing data in the buffer. So this one here, fetch the first or P1. Then after that, the second block B or P2 here, simultaneously fetch the next one. Then while I'm done processing the second block, working the second block, I can use the first block in order to fetch the next one, and etc. Okay, that's what we're doing. Of course, we don't have a double buffer, but we have a large buffer here, so we can use this one in order to speed up the access. Let's compare the time, processing time using the double buffer compared with the naive solution when you have only single buffer. we're going to use the same notation. P is going to be the time in order to what? To process the block. And R is going to be the time to read one block. And we have n blocks here. And we assume that the time to read the block or process the block is going to be exceed the time or greater than the time that required to read the block. Okay? So in this case, what we're going to do here, first, you have to read the first block. Right? Then after that, you're going to perform what? The time is going to be, of course, you are going to read the second block, then process the first one. Then you're going to read the third block, you say here, and process the second block, answer. But this time going to be dominated by what? The processing time. So it looks like here in this case, I need to process n blocks. So read the time to spend only to read one block, then after that, n multiply the time spent in order to process entire blocks. So this one compared to the n multiply R plus P, you see that using double buffer is going to be much faster using, or more efficient using, the single buffer. Yeah. The other thing here we can think about how can you can use a disk array, okay? Either gonna using multiple disks or maybe use sorry, if you have a multiple disks here. So you have, for example, you have a disk 1 and this assume that you have 3 disks here. So here you have a multiple disk here. You can perform reading here, writing here, or reading, writing here. Alright? So you're gonna increase the data rate because you have, for example, if you read the data from multiple disks, it's gonna be more efficient and more fast because it's gonna have a multiple output. Okay? Of course, you need the time in order to manage the hash time from based on 3 disks, but it's gonna be compared much faster if you try to access the same data from the single disk. Block striping here, one technique, use this one. Okay, since we are using multiple disks. In this case, or this technique, you're going to store the blocks of the file over multiple disks. Assume that we have 2 disks to simplify the process. Striping, what does that mean here? For example, I'm going to store, for example, block 1 up to block 100 here, then a block 101 up to block 200. It's going to be stored here. So if you want to access the data from P1 or P100, use disk 1. If you want to access P101 up to 200, then use disk 2 here. Okay? High read and write speed. Because it just looks like you, distribute your data among, let's say, different disks. The other one is called mirror disk. Or let's say RAID. I think RAID 0 or RAID 1 is mirror. I don't recall, but I believe one of them is going to be RAID 0 or RAID 1 is a mirror here. Okay, anyway. In the mirror here, what does that mean? I'm not going to distribute the data among different disks. No, I'm going to have the exact copy distributed everywhere. So it looks like store the data, the exact data on disk 1 and the disk 2 and the disk 3. Or disk 1 and disk 2. Now, when access the data, suddenly we have different places to access. Block 1 from here, maybe access block 2 from there. Yeah? But it's going to be, read operation going to be n times faster, depends on the number of blocks, the disk that we have. But the writing operation going to be what? As same as one disk. Because you are going to perform one disk, updating in one block or one disk, then you need to propagate the change to the other disks, right? Or you can use RAID, it depends on which is called redundant arrays of inexpensive disks here. It looks like you can use multiple disks. It's going to be software and hardware, which allow you in order to have, we do have the different levels, depends on different servers that you're looking for different solutions. Each of them have a different cost. I believe you covered this one in the already system. Here's just the goal here. We have many techniques in order to speed up, the access the data or reduce, the disk input order operation here. Or in other words, to minimize or lower the time it takes to read write data from the disk. Another thing you need just to take a look at the way that how the methods for improving the reliability of the disk here. Okay, so I'm gonna go over this really quick because it's not related to the database, but just give you an idea. There's some techniques in order to handle the disk failure. And one of them, the disk is okay, but the problem, it looks like you have intermittent, okay, or discontinuous reading, writing failure. You read something from the disk, but you need to try multiple times because maybe the structure is bad, corrupted, so you have to perform this operation multiple times until you manage to read the data. Or you write your data on a specific sector or set of sectors, and since the sector is bad, sometimes you need to make sure, you need to check whether the data has been written correctly in the disk or not. So you have to perform some kind of verify here. Another part of it in the disk, it might be have a media decay. What does that mean? In this case, the disk can be source worn out. So there's been you cannot store the data on the sector, the set of sectors. So in this case, you can do what? So the system somehow can mark this sector as unreachable, not used anymore, not available, in order to what? That means next time we try to store the data, the system say, don't store anything, or don't access or modify or store any data into this set of sectors because they are bad, are not worn out. You cannot store any data. It's not going to be valid anything. This one is going to cause the size of the disk can be reduced, right? Because we have 1 giga, then if you have bad sectors. And my times when you work in the disk operating system, we have 2. Bad sectors got a nightmare. You store your data, when you try to retrieve the data, you're gonna almost cry because you lost all your data. It's not, the bad sector is gonna be like common problem at that time. Okay? We have a permanent failure, which is the one someone got, in this case, the disk crash, which happened in my time. Now the disk is gonna be more sustained and against this kind of errors or mistakes. But in my days, if you try to move your hard disk, or say the computer from one place in another place, done. Somehow you just wave your computer, move your computer, then it looks like the hard disk is like looking for the moment that you move your computer in order to what? In order to warn the entire hard disk, or maybe the disk or the header is going to be maybe touch or scratch the platter, then done in this case. I know it's bad. It looks like they have bad quality at that time. Anyway, this is out of the mission, out of the scope of the database management system, but there's many techniques that can be followed in order, do in order to improve, the reliability of the disk. Those are techniques here, as I mentioned, can be like, this is just how to do this one. One way how to handle the disk crash that we have, like the exact copy memory, or maybe have a RAID, we have an archive. So you have, extra copy. Right now we're using mainly the cloud. So we have, other options where you can store data, or you can, recover your data, but we have like a privacy or security concern here, because it looks like, how can you trust the cloud with my own data, and etc. That's a different story. So that's all about the first part for today's lecture. We went over, as I mentioned, secondary storage, mainly talk about the disk, I'll talk about the access time, and hopefully give you an idea now. You can, imagine when you said, if we try to retrieve the data from the disk, that's a problem. We try to minimize, the access time to the disk, because the access time to the disk, or fetching the data from the disk, is expensive operation. Okay? So should be avoided at all means. Okay? And also try to avoid what's called random access data, or store the data in random. So it looks like this one's gonna just help us in the second part of today's lecture to think about how the data, or the database management system, is going to be handle large amount of data, how it's going to be stored the data on the disk, how they lay out in the disk in the way that, in order to minimize the effect of access the data on the disk. Even if we try to, I'm required to access the data on the disk, because we cannot put all the data on the main memory, right? The buffer pool has a limited space. So in this case, somehow we need to have like a smart, efficient replacement policy in the way that keep, all the blocks that need or frequently access in the main memory, and get rid of the blocks that may be rarely used. That's going to be one way. In other words, to try to minimize the time that when the query looking for the data wasn't available in the main memory. Okay? This I think available, this one. There's a chapter here in the reading part, so you can take a look to the data storage in more details. Okay, it can be the reading folder assigned. The subsection, you can read all of them. Although you didn't need anything, because they cover the most important thing. I give you like 2 places. You need to focus on the exam, and hopefully you get the idea from this whole thing. Storing the data on the disk is expensive. We try to reduce the access time to the disk, and you know the reason why behind that. Okay? So now let's take a look in more details about the first problem here. So again, as I mentioned, in this course, This course is about what? To learn how to build the software that manages a database in general. All right? Okay. So this, the reading. If you want to reading different material, different resources, if you want to learn more about this, chapter, get more details. All these text box, just I suppose not to say that. Copy the title. Definitely gonna find the title available online. For the first one, I will provide you with the second one is available online. Okay, the first one will gonna be in the reading part because it's available. All the chapters available online. Okay. So let's remind you we work in the desk-oriented database management system, where the data can be completely stored in the desk. The data can be organized into what? As a file, or say as pages, blocks, and then can be stored in the desk. The high level of the query engine gonna say, I need the page file. The system first, database management system, gonna check the buffer pool. Do you have the page file? Yes. Then gonna return the block. The address of the within the memory address to this one in order to handle, in order to process the operation. Done. If it's not, now the buffer pool is gonna find a way in order to, do you have a space in order to fetch a new page or not? I do have. Great. So what you need to do here, how can you fetch the page? So I have to go to the desk, fetch the page in the main memory, in the buffer pool, then return, the address, or memory address to the query engine in order to proceed. What if I don't have a space? So the buffer pool is going to say, okay, I need to find victim page to evict to free space in the buffer pool. Yeah, because the buffer pool is going to be limited space. We're going to see next lecture. So in this case, the system is going to say which one the page I need to get rid. We need to find out a smart way to perform the replacement policy. I don't want to, for example, to remove or get rid of the page that you use in the index, for example, the root of the index, or the page is going to be most frequently accessed page. If you get to this one, this means you're gonna maybe next operation you need to fetch it back to the desk. So that's why I said, remember I said we need to come up with some data structure or say technique, mechanism in order to what? In order to minimize the stall that when the query looking for the page and the page wasn't available in the main memory in order to speed up the processing the data here. Okay? So the system design goal that we have here is what here? We try to come up with the database management system that support what or manage a large amount of data that exceed the amount of memory available. That's what we have. If the data page can fit in the main memory, then we don't have a problem. You can fit to the main memory, then you can process the whole thing. Okay? So again, here the high level, or the goal here is to allow the database management system in order to handle the amount of the data that exceed the amount of memory available. Okay? Since in this case cannot fit the entire database main memory, there is from time to time when try to operate on a page, there's a need in order to fetch the data from the disk, reading and writing the data from the disk to the buffer pool. We mentioned that the reading and writing operation is expensive. We try to minimize this one. If we manage to get rid of all of them, that's perfect, but we can't because the size is different. The large data is large and the main memory is not enough to hold the entire data. Okay? So in this case, as I mentioned here, since we have exchange data back and forth, we need to find a way in order to not end up with performance degradation. Okay, you need to find the way in order to minimize the stall when someone acquired looking for the page wasn't available in the main memory. We need to find a way. Here go. Either going to be make it faster or make the query maybe our database management system processing another query at the same time in order to manage all the resources. Okay. Random access in the disk is usually much slower than the sequential access in the disk. That we know that. We understand, we measure that how the data, sequential data can be stored, or the data can be sequentially stored in the disk. At the same time, we look at if the data can be random, and there is no that for sure. Access data or the access time, it could be the access time to the data sequentially is much faster than if you try to perform this one using the random access. Okay. We talk about the disk again, the disk operating system. The disk-oriented database management system here. As I mentioned, the data can be stored in the disk. Someone is going to say, why you repeat yourself? Yeah, I'm going to keep repeating this one because this is a very important thing, okay? The data can be stored in the disk, And the data in the it's gonna be the file or the data in the database file. If you have a relation, you need to store this relation in the disk, all right? So it's gonna be organized as a pages or blocks. I'm gonna use a page or block, the same, yeah. They're interchangeable because in myself gonna be mean the same thing, okay? Some texts say since the data gonna be stored in the disk, we call this one a block. When you fetch this one in the memory, we're gonna call this one page. I don't distinguish between them. Page block the same, okay? So anyway, you take the file, relation R for example, you divide this one into blocks, and you're gonna store this block in the disk. Good. And with the first page being gonna be called directory page. We're gonna talk about this one. What do you mean this one? Because when you store your data on the disk, you're not gonna store this one just randomly. You need to figure out a way. How could you find the page, whether pages exist or not? You need to find a way of like data structure, come up with the data structure, will tell you, for example, where the page that belongs to this file that has enough space to store this data. How could you retrieve or navigate or iterate over every single page that belongs to this relation? Remember, when you store your data and files, you don't have a single file. You have multiple files, multiple or many relations, many data. So that's why we're gonna use the page directory in order to organize the data. More gonna be covered hopefully today. Hopefully, yeah. More details about what do you mean by page directory. But the things he somehow help you to organize the data, to fetch the data, to keep tracking to the blocks that belongs to this relation or each relation. Okay. In order to work with the data here, we have to fetch the data to the buffer pool. The buffer pool here in this case, why I need to manage or talk about the buffer here just to show you that we're gonna rely on the database management system in order to take this operation. Because someone is gonna say, oh, it looks like you're gonna perform virtual machine. Virtual memory. Because I'm teaching, security class, we use virtual machine. That's the reason the conflict. Confusion. Anyway, you have to fetch the data from the disk here, and the data gonna be something like this. Remember last time we said you had the blocks here. You fetch this one to the buffer pool. Okay, who's gonna manage this operation? Fetching the data back and forth from the disk to the buffer pool is the database management system. Why we cannot rely on the operating system? Someone is gonna say, it looks like you talk about the virtual memory. Fetch something in the virtual memory. Why don't you rely on the operating system to take care of this one? The problem here, or the main difference is, the operating system doesn't know anything about the data. The operating system, we're going to see this one later when you go deeper with the query processing and more details. When you store the data, how can you perform a process on a query? You see that sometimes if you rely on the operating system, you're going to have an issue, many problems. One of them, the operating system only handle or see the data as a sequence of bytes. The database management system is the entity who creates this data. The entity can understand, can decipher the content of these sequence of bytes into, for example, record and fields. For example, assume that you have a student ID and name, okay, and GPA. You want to store this information on the disk. For the operating system, say block, and this block has a sequence of bytes. When you say, for example, I'm looking for the page that contains specific data, the operating system tell me directly which page I can fetch it. Which one contains, I don't know. Because I don't know how what's going on inside this page because I don't know the content. Okay? So we're going to rely on the buffer pool manager in order to handle this operation. Okay? Another thing, we don't rely on the buffer pool here because in the operating system to handle this operation, fetching the data back and forth from the disk to the main memory, because in this case, we do have like a better replacement policy. Since actually, for example, based on the database management system, by looking to the data or the blocks in the main memory, of course, by the help of some extra metadata, you can specify, oh, this page is very important. This page must stay in the main memory. If you rely on the operating system doesn't know anything about the content of the data, so it's going to use the replacement policy, designed by the operating system. I didn't know about anything about the content of the data, so maybe gonna get rid of the page that I need, or most frequent access page. Always, most frequent access page must reside in the main memory most of the time. Especially, for example, you try to again use or access, say, an index. If you try to build the index, we're gonna see this one later. Usually, let's say you use a B tree in order to build the index. We have a root, and the root you have like a children, and children maybe have a non-leaf nodes. Then you have a leaf nodes. We have the record ID and the pointer to the actual record. Okay, so this is always very important. Every time you want to access or use this index, what you need to do here? You need to do what? Start from the root, access the data from the block, and the root is going to tell you, for example, whether you're going to subtree this direction or this direction. You see, that's very important here. So since I'm using the index more frequently in the system, or during the execution, at that time, or at specific time, or given time, this block must be residing in the memory, must be in the buffer. Otherwise, every time you need to access the index, I need to fetch this one. They're not costly, bro. For the operating system doesn't know this is important. So what I'm gonna do? I'm gonna get to this one. Now I need to access. That's the problem. So that's why if you hear this one before, usually in the buffer pool we have maybe the two levels. The upper level of the index is going to be reside in the buffer pool. So this one and this one going to be available in buffer pool in order to speed up the access to data. Okay. Another thing, the database management system knows, better way or correct order. How can you flushing? The dirty pages to the disk. What do you mean by the dirty pages? We're going to see later when we talk about the buffer pool. We have one page, maybe you're going to specify a set to say a bit specific Excel bit metadata in order to tell me this page is dirty page. What does that mean, dirty page? That means the page has been modified since the last time you fetched to that main memory. Okay. Another thing we have when we talk about the cache recovery later, we're gonna have what? We have like special, let's say, blocks that contains the log engine. And based on the log, let's say, recovery technique or mechanism, some of them are required to perform. Right now, you have to flush that. You have to keep reflect whatever change you have in the disk to the main memory right now. And if we rely on the operating system is gonna say, no, wait, it's still not 4. You need to wait until this one gets be 4 and another fetch. So you see that you have a different, technique and mechanism. Specialized prefetching. The database management system knows better about the content of the data. So we're going to see later, we compare the processing for, simulate the process, for example, what if we rely on the database, what if we rely on the operating system. We see that if we try to perform the prefetching, maybe the database management system is going to do a better job because you know exactly what about the content, can decipher the content of the blocks. For the operating system, randomly, or let's say blindly, just fetch all the blocks, which maybe I don't need them. Okay? In other words, I like this one, is the operating system is not your friend. Yeah, it's your friend just to operate to return off the your computer, but no, not your friend based on the database management system. But in the low level, when you try to fetch specific page, in the low level operation, I'm gonna rely on the operating system. Because remember, if you try to access, assume that you have a Linux system, and the lower level says I need to access specific page or block. So the database management system is not gonna communicate with the kernel. The kernel try to fetch whatever the data that you're looking for, or based on the low level of the operating system, gonna say, okay, fetch the data. In other words, now you have to move the spin, make the drive or disk spin. Now you have to move the read on into the correct cylinder. It's not the database management system job. So in the low level, the operating system is going to evolve to fetch the data. But who's going to control the whole process? You're going to see next lecture. The database management system is going to handle the whole operation. Make sense, guys? Good. So, since we didn't have time, okay, so this is the end of today's lecture. Hopefully see you in person next week. Please stay safe.